Okay, this is the second part of the analysis of compounds, uh, mixtures, and pure substances. And in this part, we're just going to be doing some example problems and showing you how to approach them. So here we're going to analyze a mixture of copper 2 sulfate and copper 2 sulfate pentahydrate has a mass of 1.245 grams. After heating to drive off all the water, the mass is only 0.832 grams. What is the mass percent of copper 2 sulfate pentahydrate in the mixture? So this is a pretty tough one. Let me draw for you what we have going on. So this is my mixture. We have two solids, and we have copper 2 sulfate, and we have copper 2 sulfate pentahydrate. Now, you know for darn sure that these two aren't separated so evenly in the mixture that we can just put a dividing line in there. I just put the dividing line in there so that you can see that there is what looks like to be more of the copper 2 sulfate pentahydrate, but I don't know if that's the case. Now, when we heat this, what's going to happen is this. This remains as copper 2 sulfate. This part turns into copper 2 sulfate without the hydrate, and the 5H2O ends up over here. So it somehow escapes the container. And it escapes the container because the H2O turns into a vapor, which dissipates. Okay, so really we have two things going on in here. The copper sulfate, when you heat it, is turning into copper sulfate. So there's no mass change when you heat copper 2 sulfate. However, when you heat the copper 2 sulfate pentahydrate, you turn it into copper 2 sulfate plus 5H2O. So here there is going to be a mass change between what you start with as a solid and what you end up with as a solid. This goes off as a gas, and so this is lost mass. So here, what's happening here is we start off with 1.245 grams of the mixture, and afterwards we only have 0.832 grams left over. Okay, so what does the mass of H2O have to be in this reaction? The difference of these two. So if I take 1.245 and subtract from that 0.832, we get 0.413 grams. So I know that there is 0.413 grams of H2O in my copper sulfate, right? All right, so let's see, what can we do with that number? Well, with that number, we can figure out moles of H2O. So we get 1 mole of H2O per 18.02 grams of H2O. And let's see what we get here. So 0.413 divided by 18.02. And that's going to be 0.02291 grams of H2O. Okay, so I'm thinking to myself, how does that help me figure out how much of this was in there? Because really, when they say, what is the mass percent? I kind of started this wrong. I looked at what was happening here, but I forgot. You know what? That's not the question here. Not how many grams of H2O. What is the mass percent of copper 2 sulfate pentahydrate? So what is the formula for that? Well, the mass percent copper 2 sulfate pentahydrate is going to equal the mass of copper sulfate pentahydrate over the mass of the mixture times 100%. Now the mass of the mixture we have, it's 1.245 grams. How are we going to get the mass of copper 2 sulfate? Well, you know what? I'm going to work this backwards. I'm going to put mass of copper 2 sulfate pentahydrate. Now, how am I going to get the mass of this stuff? According to everything we've been doing so far, I probably need the moles, right? Now, I see here, oh, and this should be moles. You know what? I think if I have the moles of H2O, I can get the moles of copper 2 sulfate pentahydrate. Just bear with me. Imagine we have 5 moles of H2O. How many of these do we have? 1. Imagine we have 10 mole of H2O. How many of these do we have? 2. So imagine if I have 1 mole of well, actually I'll say 5 moles of H2O. How many moles of this? 1. Because in this formula, so I'm going to move everything up. In this formula, when we say CuSO4.5H2O, this means for every 1 mole of copper sulfate pentahydrate, there are 1 mole of copper 2 sulfate, and there are 5 mole of H2O. So I can use all of these as mole ratios. So if I get the moles of H2O, I should be able to figure out the moles of copper 2 sulfate and therefore the mass of copper 2 sulfate pentahydrate. So here I'm going to take this number above, 0.022918 mole of H2O, and I'm going to multiply by 5 mole of H2O, there it is, to 1 mole of copper 2 sulfate pentahydrate. Now, what is the molar mass of copper 2 sulfate pentahydrate? Well, I know that copper is 63.55, sulfur is 32.07, and oxygen is 16, so 4 of them is 64. And I know that I have 4 waters. Waters are 18.02. So when I add these all up together, let's see what we get. So this is going to be roughly 160 plus another 75. So 160, 235-ish. Let's find out. 60 clear 63.55 plus 32.07 plus 64 plus 4 times 18.02. Now I'm going to double check and make sure that my molar mass of copper is correct. Yep. Okay. So we all add this all together and we get 231.7 grams. Okay, so I'm going to write 231.7 grams of copper 2 sulfate pentahydrate over 1 mole of copper 2 sulfate pentahydrate. And that'll give me the grams of the copper 2 sulfate pentahydrate. So I'm going to multiply this number by 0.022918 and divide by 5. And we get 0.0045836 grams of copper sulfate pentahydrate. Okay. So now what do we do with this number? We plug it into this equation here. So the mass percent, and I'm just going to write hydrate, is going to equal 0.0045336 grams over the mass of the hydrate, 1.245 grams, times 100%. You know, this number seems really small. I'm going to be honest with you. And I think I may have made a mistake somewhere, and I'm not sure where. Let me check through the problem again. That number seems correct, right? Don't those two seem to add up to that? This divided by that seems pretty appropriate. Let me do that one again just to check. Okay, 0029. Okay, that checks. And 0029 times 231. That's a check. And divided by 5. Okay, so here's my mistake. I didn't estimate this one. I just threw that number out there. This is incorrect. And here, let's try and estimate the answer now. How many times does 5 go into 231? Well, I know 5 goes into 100 20 times, so 231 40 times, plus 5 will go into that 6 times, right? So we're talking 46. So I have 46 times 0.022. Now, just think about that for a moment. 0.022 times 46. Is there any way in the world it's going to be less than 0.022? Because that's what this number is. So that's ridiculous. Now, on the other hand, is this roughly 0.02 times 50? So I lowered that one and I raised that one. I like it. So I'm going to move the decimal over 2 times here, 2 times here, and I basically have half of 2, so the answer should be around 1. All right, so I plug this into my calculator. I get 1.062 grams. This is 1.062 grams. And then we divide by 1.245. And we end up having 85.3%. Okay, so the one time I didn't estimate my answer, I plugged numbers into my calculator and I got the wrong number, and I just went with it as if, well, everything my calculator does is correct. The calculator is only as smart as the person using it. So I just thought that number seemed really weird considering these numbers we had before, and that's why I checked it. Okay, so there's the mass percent. Let's look at another analysis of a mixture. Sample of limestone and other soils is heated, and the limestone is decomposed to from calcium carbonate to calcium oxide and CO2. This is in fact one of the ways that you make cement. You use a lot of calcium oxide in cement. And so you take this limestone and you heat it up and you heat it up and you heat it up, and you drive off CO2. It's been estimated that cement production in the world accounts for about 8% of the carbon dioxide emissions in the world. 8%. So what is the way to prevent all of that carbon dioxide? Well, you can't not do the reaction, because you need to do this reaction to make cement. So you're going to make CO2, period. So what can you do with that CO2? Well, one of the things that they try to do is they try to sequester it. And sequestering, it means that you just pump it underground into some big, deep hole and leave it there. It doesn't always work so well. What else can you do with it? Well, it turns out that maybe you should think about building things that aren't made out of cement. You know, if you build things out of logs, you don't need cement. Now, of course, some of the problems are that, tall buildings tend to be made more out of concrete than out of wood. You ever seen a 40-story wooden skyscraper? No. So there are limitations to that. All right, so enough of the aside. So we have a 1.506 gram sample of the limestone, gave 0.558 grams of CO2 in addition to calcium oxide after being heated. What is the mass percent calcium carbonate in the original sample? Okay, so this says limestone containing material, which is kind of the key, that we have a mixture to begin with. So we don't have pure calcium carbonate. We only have limestone with calcium carbonate, or I should say, a material with limestone that is calcium carbonate. So let's start this one off correctly. What is the mass percent calcium carbonate in the original sample. That's where we should be starting. So how do we do that? We start off with the formula. Mass percent calcium carbonate is equal to the mass of calcium carbonate over the mass, and here, since they say material, I'm going to put material times 100%. So here we're going to need the grams of calcium carbonate, and we need the mass of the material. Now the mass of the material, they say, is 1.506 grams. So how are we going to get the grams of calcium carbonate? Well, what I'm going to suggest is that we take here the grams of CO2, turn that into moles of CO2, turn that into moles of calcium carbonate, and turn that into grams of calcium carbonate. So let's go through this pretty quickly. 0.558 grams of calcium carbonate times 1 mole of 0.558 grams of CO2 times 1 mole of CO2 to 44.01 grams of CO2 times, according to the balanced reaction, 1 mole of calcium carbonate to 1 mole of CO2. And then the molar mass of calcium carbonate, we're going to have to figure out. Calcium is 40.08. A carbon is 12.01. And 3 oxygens is 48. So we get 100.09 grams of calcium carbonate to 1 mole of calcium carbonate. And that'll give us the grams of calcium carbonate. So let's see. Learned my lesson. Not going to do it again. 0.558 times 100 is 55.8. 55.8 divided by 44 is going to be something like 1.25. Okay, so 0.558 times 100.09 divided by 44.01, and I get 1.269. And here 3 zig figs. So I'm going to go ahead and keep this little extra one around. And this is grams of calcium carbonate. And so here, the mass percent is going to be the 1.269 grams of calcium carbonate per 1.506 grams of material times 100%. Now remember, this only gets 3 zig figs, so when I'm done, we round to 3 zig figs. And this gets 3 zig figs. I should have put the arrow here because of the 558. And so 1.506, and then times 100, and we get 84.3%. And this means 84.3 grams of calcium carbonate per 100 grams of material. Okay, so that's stuff that's pretty rich in calcium carbonate. And let's do another analysis of a pure substance. Naphthalene is a hydrocarbon that once was used in mothballs. Funny story here. We went to visit my grandmother's house, and we never went there but maybe twice a year. And we're running around the house. And it turns out that we get into this one closet, and she's got this box of candy right there in the closet. And I'm thinking, I was like, 4 years old. And I grabbed this piece of candy and I popped it in my mouth. And I was just a horrible smell, horrible taste. It was a mothball. Mothballs look like candy. Okay, but they're not candy. So at any rate, hydrocarbon used in mothballs, if 0.3093 grams of the compound is burned in oxygen, 1.062 grams of carbon dioxide and 0.1738 grams of H2O are isolated. What's the empirical formula and what is the molecular formula? Okay, so let's give this a try. So you'll notice that the mass of the compound really doesn't matter here. What matters is that we have this, okay? So let's take a look here. We've got 1.0620 grams of CO2 times 1 mole of CO2 per 44.01 grams of CO2 times 1 mole of carbon to 1 mole of CO2. Now, if you really wanted to practice this, you would be pausing this video, doing this work, and then you would pop this up and look and see what I was doing. Okay, so I'm going to estimate again. This will be about 0.02 something. 1.062 divided by 44.01, and we get 0.02 something, 413 mole of carbon. So I'm not going to carry an extra significant figure. For these problems, you usually don't need to. So 0.1739 grams of H2O times 1 mole of H2O per 18.02 grams of H2O times 2 mole of hydrogen to 1 mole of H2O is equal to, and if you leave these calculations off of your exam, you're going to lose a lot of points. On the exams, the right answer is not what I'm looking for mostly. I'm looking for the ability to see how you're thinking. If I can't see how you're thinking, you're going to get very little credit. Okay, so 0.1739 divided by 18.02 and then also multiplied by 2. Now I didn't estimate, but this over this is less than 1/10. It's about 0.01 times 2, so I should get about 0.02. And here I get 0.0193, and then 0 mole of hydrogen. So now I'm going to do this. Carbon, 0.02413, hydrogen, 0.1930. I like to do it this way rather than putting the ratios. I missed a 0 here. Did you see that? So I'm going to divide by the smaller of the two. And let's see what we get. Divided by 0.02413. And we get carbon 1.250, hydrogen 1. So what multiplier do we want to use so that we get whole numbers? I'm thinking 4. So 4 times this ends up being 5. 4 times this ends up being 4. So this is the empirical formula. Okay, now how do we get the molecular formula? What we're going to do is we're going to take this information here. The molar mass is 128.2. 128.2 grams per mole. And we're going to divide by the molar mass of this. 5 times 12 is what? 60.05. 4 times 1.008 is 4.032. Add the two together and you get 64.08. So 64.08 grams per mole. And here you can see that even if we don't get 2 exactly, it's going to come out really close to 2. So the factor is 2. Or we should say really multiplier. So we get C4, or excuse me, we get C5H4 with our multiplier of 2, and we get C10H8 is the molecular formula. And there you go. Here's another analysis of a pure substance. This is one with carbon, hydrogen, and an oxygen. So remember, for this one, we need to get the moles of carbon, moles of hydrogen, grams of carbon, grams of hydrogen, grams of oxygen, then moles of oxygen. So let's give this one a try. I'm going to go through these more and more quickly. And remember, you can always pause the video. And the idea here is that you want to be giving this a try on your own. And then you can turn the video on and kind of fast forward it to where I get the answer and see if we get the same thing. But you also want to compare the work that I do compared to the work that you do and see that it's very similar. So here, I'm going to go ahead and list these things so that you know exactly what I'm doing. So here, the moles of carbon, we're going to start off with 0.1356 grams of CO2 times 1 mole of CO2 per 44.01 grams of CO2. Now at this point in time, you may be tired of writing this all out every time, and you might be wanting to take shortcuts. And you know what, if you're doing your homework, that's fine, but on the exam, that's not okay. You're only doing one of these problems on the exam. I need to see all the work. So get in the habit of showing your work each time. It builds good habits. Okay, and then we have 1 mole of carbon per 1 mole of CO2. I'm going to set up the next one. The moles of hydrogen are going to be 0.0833 grams of H2O times 1 mole of H2O over 18.02 grams of H2O times 2 mole of hydrogen to 1 mole of H2O. And let's go ahead and calculate these numbers. 0.1356 divided by 44.01, and we get 0.003081 mole of carbon. And here we get 0.0833 divided by 18.02, and we get 0.004623 mole of hydrogen. Now, one of the things that math teachers hate, and I really don't like either, is that you take this and you convert that into grams, and so you write something here. And technically it is correct, but it isn't a good form of communication. So what I'm going to do is I'm going to bring this down, and I'm going to put grams of carbon, 0.003081 mole of carbon times 1 or 12.01 grams of carbon to 1 mole of carbon. So the only difference between writing this up here and writing this down here is I've written this extra amount of material, which takes 10 seconds. So that's not a waste of time because it's very neat. You can see what I'm calculating here. And here for the grams of hydrogen, I'm going to have 0.004623 grams of, mole of hydrogen times 1.008 grams of hydrogen per 1 mole of hydrogen. And let's see what we get. Here we get 0.004660 grams of hydrogen. And here we get 0.003081 times 12.01. We get 0.03700 grams of carbon. And that seems about right for both of these to me. And then what we're going to do is we're now going to get the grams of oxygen. So I'm going to put my work up to here. And I'm going to put the grams of oxygen is going to equal 0.0956 grams minus 0.03700 grams and minus 0.004660 grams. So let's see what we get here. 0.0956 minus 0.0370 minus 0.004660. And the way I kind of look at this is like 9.5 minus 3.7. So that brings it down to what? That's almost like minus 4. So that's a 0.5-ish, 0.55-ish. And then here, that seems to be about right because that's so little that I'm going to ignore it. So the answer should be around 0.05, and I get 0.0540 grams. Now look at my calculator. It actually doesn't put a number after the 4. See that? There's no number after the 4. So if my calculator doesn't put a number after the 4, what is that number? It's a 0. Now I know that this number's good, this number's good, and this number's good. It's good to 4 places past the decimal. So that means my answer should be good to 4 places past the decimal. This is good to 5 places past the decimal. So who's the winner? 4 or 5? 4 places because it's less precise. So that's my grams of oxygen. And then the moles of oxygen, I'm going to get by doing 0.0540 grams of oxygen times 1 mole of oxygen per 16.00 grams of oxygen. And let's see what we get. I get 0.003375 mole of oxygen. So let's put it all together. Carbon, 0.003081 mole. Well, we don't need the mole there. Hydrogen, 0.004623, and oxygen, 0.003375. So what do we divide by? I'm going to divide by 0.003081 and get carbon 1, 0.003081. And here I get, oops, I know I did something wrong here. I get 1.5 and 0.003375 divided by 0.003081. And we get 1.095. Now, looking at the specificity of the data, how well it is, I don't like the idea of saying that that's 1. So what I'm going to do is I'm going to multiply everything by 10. This is a common thing to do. Now that looks a lot closer to 1, a whole number, than otherwise. So I think maybe the formula is C10H15O11. Okay, so I'm thinking that might be the empirical formula. Now let's see if I'm right. They say the molar mass is 62.1 grams. Well, I'm thinking that maybe I jumped to a conclusion here that I shouldn't have. What is the molar mass of this? It's way more than 62.1. So clearly I went off scale here. So maybe it is C2H3O, and this is supposed to be 1, 2. So let's try that for the empirical formula and see if it works out well for the molecular formula. So for the molecular formula, we're going to take our molar mass of the molecular formula divided by the molar mass of the empirical formula, and hopefully we're going to get that multiplier that we want. That's a whole number. So we have 62.1 grams per mole. And what is the molar mass of this? Well, 24 plus 3 is 27. 27 plus 2, or plus 32 is 59. And that's pretty close to 1. So I'm thinking that may be the empirical formula too. Now, usually you end up with tighter numbers than this, and I may have made a mistake somewhere. So let's see if we can isolate if there are any mistakes. So here we have the 0.135 divided by 44, and I think that seems about right because 4 goes into 13 about 3 times. Here, 1.8 or 2 goes into 8 about 4 times, so that 4 seems right. Here, 0.003 times 12 means I should move the decimal over 1 time, and I get that. And 0.004 times 1 means that should pretty much be the same. Here, when I subtract these numbers from this one, this seems about right. For oxygen, does 16 go into that? 0.0033 times. Well, 1.6 goes into 5.4 about 3 times plus. So yeah, that seems about right. Okay, and then I'm going to just double check that number and see if 0.054 divided by 16 is, yep, that's good. Okay. So apparently this number divided by that number, we should be thinking that that's close enough to 1. And here, the thing that you need to remember is looking at the problem, if the molar mass is this, what is the molecular formula? Clearly, when they got the molar mass, they were a little bit off. Okay. Now this is the last one, I believe, the last sample problem. And this is an analysis of a pure substance where we're trying to find the empirical formula, but this is not your normal combustion reaction. So let's see how we deal with one like this. Nickel forms a compound with carbon monoxide. So you have NiXCOY, where X and Y are whole numbers. To determine its formula, carefully heat 0.0973 gram sample in air to convert the nickel to 0.0426 grams of nickel 2 oxide and the carbon monoxide to 0.100 grams of CO. So let's see what that reaction looks like. So this is the sample, NiXCOY. We're going to heat it up in air. So maybe this reacts with oxygen. So I'm going to put O2 here. And we get NiO plus CO. Now, we don't really need to worry about a balanced reaction. Here's the deal. We get 0.100 grams of CO2, and we get 0.0426 grams of nickel. Now, the important thing here is to understand that every single nickel atom here became a nickel atom here. So we can take our grams of nickel 2 oxide, turn that into moles of nickel 2 oxide, turn that into moles of nickel, and that is equal to the moles of nickel in NiXCOY. Also, if you take your so this is 0.0426, if you take your 0.100 grams of CO, that will give us moles of CO, which will give us moles of carbon, which can be used to get moles of CO2 in NiXCOY. Oh, this should be mole 2, 2, and this should be CO. So let's see how it works. 0.0426 grams of nickel 2 oxide times 1 mole of nickel 2 oxide. And to get the molar mass of nickel 2 oxide, I need the mass of molar mass of nickel, which is 58.69. 58.69, and then plus 16 for oxygen. 74.69 grams times 1 mole of nickel to 1 mole of nickel 2 oxide. And I know it's 1 to 1 because the subscript here is 1. Now we have 0.100 grams of CO2 times 1 mole of CO2 per every 44.01 grams of CO2 times 1 mole of carbon to 1 mole of CO2, because you can see that in the formula here, there's 1 carbon for 1 CO2. And then we can also write 1 mole of CO to 1 mole of carbon, because you can see there's 1 carbon and 1 CO. And that'll give us the moles of CO. Okay, so we have 0.1 divided by 44, which is going to be 0.002 something, right? So 0.1 divided by 44.01, and sure enough, 0.00227 mole of carbon monoxide. And up here, how many times does that go into that? Well, 1, 2, 3, it goes in about 6 times, right? 0.0006. 0.00, and let's see what we get. 0.0426 divided by 74.69. Okay, 0.000570 mole of nickel. So I'm going to say nickel, 0.000570, CO, 0.00227. Divide each of these by 0.000570. And we get nickel as being 1 and CO as being 3.98, which is certainly close enough to round to 4. So here's the compound. All right, thank you for listening.